Welcome all of you. So, let us get started with Cover's theorem. So, the reference to this work is the paper by Professor Thomas Cover in February 1964 and followed by a book by Nilsson on learning machines in 1965. We will begin with a brief motivation of this theorem. How do we quantify the complexity of a neural network architecture? So, if I have to do a classification task, how can I quantify the complexity of a neural network architecture? For this, we need a counting measure for a discrete set of mappings. So, this is our motivation. Suppose I want to have linearly separable patterns, or I want to ensure linear separability. How can I quantify the complexity of this design? To understand this, let us start with a few examples on dichotomies. Figure A here describes linear dichotomy because we have a hyperplane here that separates the crosses from the circles, because the discriminant boundary is a plane. We do not have to think about linear dichotomy, we can have spherical dichotomy. For example, if we observe figure B here, we have these circles that are surrounded by these crosses. One way to separate these two patterns would be to put a circle as the discriminant boundary. This is a circle and this forms our discriminant boundary. Similarly, we can think of quadratic dichotomy as well. So, we can have two patterns here which are these circles and these crosses, and we have these conics that are separating these two classes. So, as you can see, the discriminant boundary is going all the way from a simple hyperplane to a curve, right. A neural network can give you such discriminant boundaries that can be these curves, whereas through simple pattern recognition engines we can have lines as our discriminant boundaries. Throughout our journey into this module, we will assume linear discriminant boundaries. Now, let us formulate things a little bit. Consider a fixed finite set of input vectors x1, x2 so on till x suffix p, and each vector xi is a point in an n dimensional space, right. This is a point in an n dimensional space. Can we attempt to compute the dichotomies for a perceptron? This is the first algorithm that we learned, and we would like to compute the dichotomies for a perceptron. The number of linearly realizable dichotomies on the set of the points depends on a mild condition called the general position. I repeat again, the number of linearly realizable dichotomies on the set of points depends on a mild condition called the general position. General position demands that no subset of size less than capital N, which is the dimension of the input vector, is linearly dependent. So, general position demands that no subset of size less than n on these vectors is linearly dependent, and this is the notion of linear independence and dependence from the linear algebraic context. Okay. Now, with this we get towards the statement of the theorem. Let this set x1, x2 so on till xp be vectors in Rn that are in a general position. So, you should recall what general position is. The number of distinct dichotomies applied to these points can be realized by a hyperplane given by this combinatorial quantity, that is C of p comma n. I have p points and my dimension is n. This is given by 2 times summation k equals 0 to n p minus 1 choose k. Now, how do we approach solving this puzzle here? One way is to prove this by induction, but we should be very clear about boundary conditions that we carefully set up so that our result is actually valid. And why is this result useful? Because this will tell us that if you go to higher dimensions, the possibility of having linearly separable patterns is much higher. The probability of having linear separability over the set of data points increases with increasing dimension. Now, we begin with the proof. We start with p points in general position and let us assume that there are C p comma n dichotomies. The C is basically for the counting function. Suppose we add an extra point to this set, that is I introduce a point x p plus 1, then we have C of p plus 1 comma n dichotomies, right. I have the same hyperplane and I have C of p plus 1 comma n dichotomies. The idea is to set up a recursion to link C p plus 1 comma n with C p comma n. Let B1, B2 so on till B suffix p be a dichotomy realizable by a hyperplane over the set of p points. That means B sub I is minus 1 or 1 for each point xi, and there is a set of weights w, so that the sign of W transpose xi gives us Bi, right. Sign of W transpose x1 is B1, sign of W transpose x2 is B2 so on. So, I have a hyperplane W. When I take the inner product with the point, it gives me these and then I take the sign, I get these attributes B1, B2 so on till B suffix p. Using one such W, which is the weight vector, we get a dichotomy over p plus 1 points given by this tuple. So, I have for the point x p plus 1, I take the same hyperplane and I take the inner product and then I do the sign, I get B p plus 1. For every linearly realized dichotomy over p points, there is at least one linearly realized dichotomy over p plus 1 points, and different dichotomies over p points define different dichotomies over p plus 1 points because they differ somewhere over the first p coordinates. This is basically reinforcing the combinatorial aspect that we see in the geometry of this problem. Now, note that the additional dichotomy is possible by reversing the sign over the last coordinate, because we can have a plus minus sign over the point xp plus 1. With this we can infer that c of p plus 1 comma n is greater than c of p comma n, right, because we can have additional dichotomies with p plus 1 points, and let E be this extra term that satisfies c p plus 1 comma n equal to c p comma n with equality, right. There are two cases to consider here, and if we visualize, this point xp plus 1 can be on this hyperplane or it may not be on the hyperplane. So, there are two possibilities, and let us look at both of these two cases together and then arrive at our conclusions. Case A, one of the weight vectors w that generates these coordinates b1, b2 so on till b suffix p passes through the point xp plus 1. Now, but we need a sign for this. So, by adjusting the angle of the hyperplane, this is very important, by adjusting the angle of the hyperplane we can adjust the sign of w transpose xp plus 1 to be plus 1 or minus 1, right. If I tilt this slightly like this, I have one position. If I tilt it slightly like this, I have something else. So, therefore, both these tuples b1, b2 so on till bp with the last coordinate corresponding to the point xp plus 1 being plus 1 or minus 1 possible. Now, the other case is no hyperplane passes through xp plus 1, that is the p plus first point is not lying on the hyperplane. Therefore, the point lies on one side of the old dichotomy, which is pretty obvious. Now, E is the number of dichotomies over p points that are realized by a hyperplane passing through a fixed point xp plus 1. By forcing the hyperplane to pass through this point xp plus 1, we are going to n minus 1 dimensions instead of n. This is very important to note, right. I can have 10 points, all of them lying on the x axis, and the dimension is still 1 there. This is the central idea. So, geometrically, if a point is on the x axis, the hyperplane has n minus 1 axes left to work on the problem. If it is not on the x axis, then we can rotate the axis of the space to get the point on the x axis, and there is no effect on the geometry of the problem. So, the number of additional terms is essentially this counting function c of p comma n minus 1, because we are working over n minus 1 dimensions. Now, we have the recursion which is set up like this: cp plus 1 comma n is c of p comma n plus c of p comma n minus 1, and this is this extra term that we have. Okay. Now, once we are given a recursion equation, we need boundary conditions to solve this, and we have to be careful about proving these results using induction, because if we do not use the boundary conditions appropriately, we may still verify the validity of the proof of a result that possibly could be wrong. So, let us consider the boundary conditions. These are very important. We will stick with Nilsson's work here. The first boundary condition is c of 1 comma n equals 2. So, what does it mean? there is one point in Rn and can be realized by two labels +1 and -1. So, this is obvious, this condition is sort of obvious. The second condition is C of p comma 1 equals 2p. That means we have p points in R1, that is in one dimension we have p points, and the number of dichotomies that we can have is basically 2p. This is an important boundary condition, and we will see this result sort of through an example, and the result is pretty straightforward. By construction you can arrive at 2p. So, let us take p equals 3. So, we have these circles and we have these crosses. So, we observe that for all these patterns, that is 0 0, these let us say if this 0 can be a 0 and this the circle is a 0 and we have a cross to be a 1, we can enumerate through a Boolean mapping, right, all the way from 0 0 0 to 1 1 1. So, I have a circle, a circle, a circle, a circle, a circle, a cross, so on till I reach with a cross, a cross, a cross, right. Here I can put a hyperplane wherever I want. In the first case, right, I can put wherever I want. In this case I have one hyperplane here that can separate the crosses and the circles. Here with one hyperplane I cannot, because I will need two hyperplanes. I will use a different color here. So, I will need this color here. So, it is difficult for me, I have to have two hyperplanes, I cannot realize a dichotomy like this. Whereas for the next pattern, the circle and the two crosses, I can have a hyperplane, so on and so forth. So, clearly except the circle, the cross and the circle, and the cross, the circle and the cross, we can have a hyperplane that can shatter the points. By shattering I mean I have a hyperplane that can separate the points, right. Now, this is an important boundary condition, and with this we will look into the validity of the proof of the theorem. So, let us prove the result through induction. So, let us focus on our steps. The base case is C of 1 comma n. So, the number of points chosen is 1 and the number of dimensions is n. C of 1 comma n is 2 as expected, because we have the boundary condition that we discussed just before. The induction step starts with this process. C of p plus 1, we assume that result is true for dimension say m equals n, and then we look at the case. Here we are doing induction over the number of points, right. So, therefore, we have to look into the case where we bring in the number of points as our parameter. So, the base case was with the number of points m equal to 1, and then we look at the case where it holds for m equals to p, and then we consider the case for m equals p plus 1. So, the induction is over the number of points. This is very important. You can do it over the dimension or you can do it with respect to the number of points, but we will do it with respect to the number of points here. Now, C of p plus 1 comma n is basically C of p comma n plus C of p comma n minus 1, and we just expand this out. C of p comma n is 2 times summation k equals 0 to n p minus 1 choose k, and C of p comma n minus 1 is 2 times summation k equals 0 to n minus 1 p minus 1 choose k. Observe carefully the upper limit in the summation, right. This is a small algebraic detail, and at this stage the careful student should ponder about the case with p minus 1 choose 0. What does it mean? when we are at 0 dimensions. When we are at 0 dimension, it is basically a point, and p minus 1 choose 0 is essentially 1, and therefore we have again 2 possibilities there, and that is the reason why we have this term 2 here. Now let us proceed with the simplification. So we have this combinatorial sum 2 times summation k equals 0 to n p minus 1 choose k plus 2 times the summation from k equals 0 to n p minus 1 choose k minus 1. So this result, I did the simplification because I had the upper limit as n minus 1 in my previous slide, because this was n minus 1. To make the upper index also to be n, I just readjusted the k minus 1 term that is appearing here and letting this go from k equals 0 to n, right. Now this is valid, so we pull the 2 out, we have 2 summations, so we will group them together. This is summation k equals 0 to n p minus 1 choose k plus p minus 1 choose k minus 1. So this is within this braces, within the red braces, the summation is within these 2 red braces. Now we use the basic identity from elementary combinatorics, which is n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. This is the basic identity. Using this we plug in, we land up with 2 summation k equals 0 to n p choose k, which is the result what we have. And a very important note is, if you assume the boundary conditions to be incorrect, then you may land up with a different kind of expression here, where the summation goes from k equals 0 to n minus 1, and that can give you slightly wrong results when you enumerate, but if you stick with the right boundary conditions, the result is valid. But through induction you may not be able to verify the accuracy of that result. So therefore it is very important to look into the boundary conditions carefully. Now let us look into the implications of this theorem. Let us consider the probability of having a perceptron that can provide a linear dichotomy over p points. So that was our objective, right. We start with a perceptron and we want that to provide us a linear dichotomy over p points. So this probability is given by C of p comma n upon all the possible dichotomies. And if you think of all possible dichotomies, we have 2 power p possible cases, and C p comma n is less than that. Now this gives us, if we simplify, because we have the equation for C p comma n, which is 2 times summation k equals 0 to n p minus 1 choose k, we simplify this to get this probability to be 2 power 1 minus p times summation k equals 0 to n p minus 1 choose k. So this is the probability of having a perceptron that can provide a linear dichotomy. I would like you to plot this probability with respect to the dimension n for a fixed size p, that is the cardinality of the set of the points, and observe the concavity in the behavior of this plot. Okay, so this is an important implication. So what it means is we can go to higher dimensions and there should exist a linear dichotomy over those p points towards pattern separability. Now let us revisit the XOR problem. Though there is no direct implication, the idea behind Cover's theorem leads to an important consequence, and this consequence is we can use, this is the idea, we can use a nonlinear function which is also called a hidden function that acts on the input vector to lift this to a higher dimension, and we say that the input vector is transformed to the feature space by this nonlinear function or this hidden function, and typically the dimension in the feature space is greater than the input dimension, right. So, here I use n to be the dimension of the feature space and m to be the dimension of the input space with a slight change in the notations than what we had in Cover's theorem that we just discussed. Now, this is an important consequence because we can lift data points to higher dimensions, and in higher dimensions we can ensure linear dichotomy, right. This is important for us. And why we need linear dichotomy? Because it simplifies our problem, because we just need a hyperplane to solve this problem than possibly the use of a complicated neural network that can have a nonlinear discriminant boundary. Now, let us recall a dichotomy is phi separable if there exists an n dimensional vector W such that the inner product of W with respect to phi of x is greater than 0 for x belonging to class 1 and otherwise. So, in the perceptron this phi was not there, and we just had W transpose x to be greater than 0 for class 1 and W transpose x is less than or equal to 0 for x belonging to class 2, but we can bring in a dichotomy that is phi separable by involving this nonlinear function phi, right, because we are now acting in the feature space. Now, let us consider the XOR problem within this context. Okay. Let us consider the XOR problem within this context. We have a 2 variable situation here, variables x1 and x2, and they are Boolean variables taking zeros and ones. So, I have 4 possibilities 0 0, 0 1, 1 0 and 1 1, and I am marking these coordinates. The circles are with coordinates 0 0 and 1 1. So, this is one coordinate and this other coordinate, and 1 comma 0 lies here on the x axis, that is the cross, and then 0 1 lies on the y axis, and that is also this cross. Now, clearly the XOR problem is not linearly separable as is, because we cannot have one hyperplane that can shatter these points into 2 different classes. Now, let us consider the pair of Gaussian hidden functions. A hidden space is also a feature space, and we use this terminology interchangeably. Sometimes we say it is hidden space, sometimes we say it is feature space, sometimes it is a hidden map, sometimes it could be a feature map, but both mean the same. Let phi 1 of x be given by this equation exponential minus norm x minus t1 square, and this point t1 is 1 comma 1 transposed, and x is also of the same size, which is a 2 by 1 vector. Phi 2 of x is exponential minus norm x minus t2 square and t2 is 0 comma 0 transposed. Now what we will do is we will tabulate these two functions phi1 and phi2 for various points of x, and in this case we have 4 points. Let us tabulate the computational evaluations of the points x over phi1 and phi2. So we have x, we have phi1 of x, we have phi2 of x. So we have 1 comma 1, we have 0 comma 1, we have 0 comma 0, and then we have 1 comma 0. So if we compute these values, you can plug this into your calculator, we will end up with 1, this is 0.135, this is 0.3678, this is 0.3678, this is 0.1353, this is 1, this is 0.3678, and this is also 0.3678. Now what would be interesting is to plot this in the phi1 phi2 plane. If you observe the points one comma 1 and 0 comma 0, they give you two different coordinates, right. You have this is 0.1353 and then a 1 here, the other is a 1 and a 0.1353, these 2 points are here, right. This is our original 0 comma 0 under the mapping, and this is our 1 comma 1 under the mapping. I just put this arrow indicating this, and both of these 2 points which I indicate in the black color, which is 0 comma 1 and 1 comma 1, map to the same point which is 0.367, 0.367. Now if you observe this coordinate system and see the points through this transformation, clearly we can have a line that can separate these points, which means using this nonlinear transformation, in this case using these Gaussian hidden functions, we are able to transform the points in the original coordinate system to points in the feature space that are linearly separable. So, this is a hyperplane and the points are linearly separable. So, therefore, this kind of motivates that we can use nonlinear functions or hidden functions to transform the inputs to points in a feature space that can provide us the necessary freedom to solve the classification problem using a linear decision boundary. Okay. So, this completes the XOR problem. So, we have seen the XOR problem revisited the second time, and here we have used a hyperplane on the feature space, and that is done through the Gaussian units. Okay. We will stop here and we will proceed further.